the title is Determined Admissible Sets. I'll introduce the main characters for today. The first one is infinite games, which is what we will be looking at. So if you have a set X, then you can define what is known as a Gale-Stewart game on X, or in a subset of X. So let A be a subset of X, and then you consider a game where you have two players, and then they take turns playing elements of X, X1, X2, and so on. And this goes on infinitely often. Actually, I guess you want A to be a set of infinite sequences of X. Then, after infinitely many turns, we say that player 1 wins the game if the sequence that was produced is an element of A. And if not, then player 2 wins. So this is a zero-sum game. It's a perfect information game. Everybody knows what the other is doing. And yeah. So when you have a game, you could have strategies for that game. So a strategy is a function, let's say sigma, from finite sequences in X to X. And it just tells you what to do in your next turn. Say you're playing the game, you have to play 2 rounds or 1 round each, and then the strategy tells you what to do afterwards. Yeah.
Is it a strategy for the first player or for the second player?
Well, it could be, you could define a strategy in abstract and then have either player follow it. Mm-hmm. In which case, the only thing that would matter would be its value on tuples of even length or of odd length. Mm-hmm. But it doesn't really matter.
So actually it's a pair of strategies. It's a strategy. Sigma includes both the strategy for the first player and the second player.
Yeah. Mm-hmm. So we say that sigma is a winning strategy for player 1 if the sequence x0, x1, so on belongs to A whenever x, I guess, 2n is obtained by applying sigma to the previous place, 2n minus 1, for all n. I need change. And similarly for player 2, it's winning strategy for player 2 if x, the sequence does not belong to A whenever all the odd stages are obtained by applying the strategy to the previous moves. And then we say that A, or the game, on A is determined if one of the players has a winning strategy. Has a winning strategy. And now the axiom of determinacy, ADX, says all games on X are determined. And so normally the forms of AD you study are when X is the natural numbers. This is the most common way, and then it's just called AD. And it says that all games on the natural numbers are determined. But you can also do it for the real numbers where they play real numbers. And the good thing about this is if X is the natural numbers, then the space X to the n is n to the n. In this space, we can think of it as the real numbers. So we can think of A as a set of real numbers. If X is the real numbers, then we have R to the n. So that's a space of infinite sequences of real numbers. But every infinite sequence of real numbers, we can also think of itself as one real number. So we can also think of this as the real numbers. You could also consider games that go on for longer than omega many steps, say omega squared. That's something we will do later. And at that point, you just need to decide who moves at limit stages, and it doesn't matter. It could be player one. Okay? So, here's a, let's call it a note. Call it a theorem. Can't remember who proved this. I hope I don't say the wrong name on camera. I think it was Michalski and Steinhaus. So they proved that ZFC plus AD is inconsistent. Because if you have the axiom of choice, then you can construct a game that's not determined by diagonalizing. So
AD is ADX for all X?
No, just natural numbers. Actually, ADX for all X is inconsistent without the axiom of choice as well. You can give examples. So AD for the ordinal omega 1, that's inconsistent. AD for the power set of the reals is inconsistent. Actually, pretty much any way you try to extend this past the real numbers is going to end up being inconsistent. So, yeah, actually we would just look at X when X is the natural numbers or the real numbers. So, but then the question was, what about if you don't have the axiom of choice here? And that turns out to be consistent, although that's not provable in ZFC. Actually, let me state that. So there's a theorem of Wooden that says that the following are equiconsistent. One, ZF plus AD. Two, ZF C plus there are infinitely many wooden cardinals. So it's consistent relative to ZFC if you assume large cardinals.
And is there AD for natural numbers or?
Yes. So AD, I'll write that. Sorry? No. So this is an equiconsistency. He also showed that if you have a measurable above, then that implies that AD holds an L of R.
Yeah. Mm-hmm.
So this is an equiconsistency, but if you assume a bit more, then you have a very natural model of AD.
Mm-hmm.
So I think of that as a result in reverse mathematics, where AD holds in L of R, but you can't prove it in theories that are not strong enough like this one. He also showed by the way, if you don't know what a wooden cardinal is, that doesn't matter for this talk. It's a large cardinal. He showed that the following are equiconsistent. 1 ZF plus ADR. By the way, ADR is not going to be weaker than AD because all the natural numbers are real numbers. So, and then ZFC plus. Now, instead of asking that there are infinitely many wooden cardinals, you could ask that there is a limit of wooden cardinals. It's the same thing. So here you want that there is a lambda, which is a limit of wooden cardinals and something called less than lambda strong cardinals. Again, if you don't know the definition of this, it won't matter for today, but you should know that this is significantly stronger than this. For example, this implies this is stronger than assuming that there's a proper class of wooden cardinals, for example. So although for this you need only omega many, for this you need more than a proper class. And then something you could ask is, what if you, instead of having ZF, you have some other set theory, such as Kripke-Platek?
And then you're saying that they're inconsistent over which base theory?
Well, these theories include both ZF. The equiconsistency, you can prove it in arithmetic, yeah. Are you familiar with Kripke-Platek, or should I say something about it?
Well, generally familiar, but maybe a few words about
Okay.
quick reminder would be helpful.
Because that's another one of the main characters today. So Kripke-Platek is the set theory consisting of the axioms of, let's see, we have pairing, extensionality, what else? Infinity, union, we don't have any replacement, well, not as part of the axioms. There's no power set. There's separation, but only restricted to sigma zero formulas. And then we have collection, restricted to sigma zero formulas. So collection says that if for all x there's a y that satisfies some condition, then if you have a set A, you can take all the x in A and find a set B that collects the y's for which that thing holds. Except now we're looking at sigma zero things. And, we have foundation. Sometimes they define Kripke-Platek with the foundation axiom, and sometimes with the whole schema of foundation. For
This is Kripke-Platek Kripke-Plattek with infinity.
Right. Yeah, I call it just Kripke-Plattek.
Okay.
And I also use the axiom of foundation, but it also won't make a difference for today. And the point about Kripke-Plattek is that it's a weak set theory, and it's weak enough that its models are nicer in general and easy to understand. And the idea is that you can lift all the recursion theory from the natural numbers to models of Kripke-Plattek. That's the general motivation. So it's a more constructive form of set theory because it's motivated by the recursion theory. And you can ask, well, what if you look at Kripke-Plattek plus AD or Kripke-Plattek plus ADR? So for the first one, you're going to get a theorem that's very similar to this. And that's because just with a little bit of determinacy, you can prove the consistency of ZFC with any finite amount of wooden cardinals. So I'll write it down. So KP plus AD proves the consistency of ZF plus the schema saying there are n wooden cardinals for all n. So you can't improve that result by a lot. And this follows from this is equiconsistent with projective determinacy, which is provable here. And the fact that this is equiconsistent with projective determinacy is a theorem of Wooden. Oh, by the way, for the purposes of this talk, let's say that AD includes a clause saying that the real numbers exist, because otherwise it's not that convenient to talk about games on the payoff sets are sets of real numbers. So AD includes a clause that says that the real numbers exist, because that's not provable in Kripke-Plattek. So you're not going to improve this much. But turns out Kripke-Plattek plus ADR is very different from ZF plus ADR. So let's call that theorem A. It's a theorem of ZFC, I guess. Suppose that there are omega squared wooden cardinals. Then there is a transitive model of KP plus ADR containing all reals. So you get a big difference there, because omega squared is in particular less than a proper class of wooden cardinals. And in the proof of this theorem, it's very easy to bundle all the set theory that comes into play and black box it. So what I want to do is go over the part of the proof that is not the set theory. And I think there should be time.
And so this observation, where does it follow from this observation part? This simple.
So there's a theorem of Wooden that says that this theory that I wrote down here is equiconsistent with ZF plus projective determinacy. And the projective sets are those that are definable over the real numbers from parameters. And in Kripke-Plattek, I mentioned that AD includes a clause asserting that the reals exist. So if you have the real numbers as a set, then you could take everything definable over that set. So all those sets, they're all determined by AD. So, to get ZFC on top of that, that takes a bit more work.
So it consists of projective determinacy that we in fact established
Right.
by AD, and then, okay.
Well, you can get consistency of ZF plus predictive determinacy. Right. You can get more. I'll say something actually. I'll prove an equivalence, or I'll state an equivalence. We'll see.
And how obvious it is that AD is simply, so does it, so how much in fact separation can one infer, not by consistency, but simply, can one infer any separation beyond sigma 0 in Kp plus AD?
Just the one you get for free in Kp. So you get sigma delta 1 separation and sigma 1 collection. Actually,
But you can build a model where full separation and collection will be as in ZF.
right, but not AD. AD will not hold in that model.
Of course, yeah.
So, yeah, it's nice. You can build many models that have many large cardinals in them, but AD is only outside. Actually, if you look at Kp plus ADR plus sigma 1 separation, that's again very strong. It's closer to this one. So you can't improve Kp much here. You can put Kpi, but so actually Kp plus AD will be to ZF plus AD as arithmetical transfinite recursion is to ZF. Maybe I can say something more. There is a theorem of Steele. It was one of the first results in reverse mathematics. That says that the following are equivalent over recursive comprehension. By the way, the things that I don't define are because they won't show up again. He showed that arithmetical transfinite recursion is equivalent to determinacy restricted to delta 1 sets. That's equivalent to determinacy restricted to sigma 1 sets. So open determinacy. And here the analog is we have an equivalence between number 2 is open determinacy. But now for games of length omega squared, and number 1 will be there is a transitive model of Kp plus AD containing the reals. And as you go over the determinacy hierarchy for games of length omega, you eventually get to Borel determinacy, which is a little bit below ZF in consistency strength. And similarly, as you go over the determinacy hierarchy for games of length omega squared, you eventually get to Borel determinacy, which is a bit weaker than this theory here. So it kind of feels like Kp plus AD fits within ZF plus AD the same way that arithmetical transfinite recursion fits within ZF.
What did you say again about Borel determinacy?
I don't remember. I think I said that
Borel determinacy.
as you go climbing the determinacy hierarchy for games of length omega, you eventually get to Borel determinacy, and that's just, in terms of determinacy, is the best you can get before you get to ZFC, or before you go past ZFC. Whereas in games of length omega squared, Borel determinacy is the best you can get before you get to ZF plus AD in terms of consistency strength. So this theory proves Borel determinacy for games of length omega squared.
There is also sigma 1 determinacy, which is strictly between, I think.
Strictly between
Full AD
Mhm.
and the Borel determinacy. So it's just one measurable cardinal.
Right. Right. Yeah, so here I'll make a drawing. You have delta 1 determinacy, then you have ZF, this is consistency strength. Then you have sigma 1 determinacy, and then you have AD here, or ZF plus AD. Well, actually you have KP plus AD. And then on the other side, you have delta 1 determinacy for games of length omega squared. Then you have ZF plus AD. Then you have sigma 1 determinacy for games of length omega squared. And then you have KP plus ADR. So that's kind of the picture. It's maybe a bit too vague, so I'll say something more precise.
So this left hierarchy, is it over RCA0 or over something stronger?
Oh, no. Let's say over ZF. Let's say over ZFC. You need a stronger base theory for the equivalence to be true. I mean, stronger than RCA0. Probably something like Kripke-Platek should be enough. Or Kripke-Platek plus the reals exist. Right, so you can't, it's a 0 by the way. If you put delta 0 determinacy, that's no longer equivalent here. Let's call this theorem B. Theorem C will be the one suggested by this pattern that is pictured in the drawings. So it's a ZFC thing. Suppose that open games, by that I mean sigma 1. Sigma 1 games of length omega cubed are determined. Then there is a transitive model of KP plus ADR containing the reals. So I'll talk about this theorem in a bit. And the part that's missing is that also ZFC. Suppose there are omega squared wooden cardinals, then this assumption holds. So that's how you prove theorem A. I'm just splitting theorem A in half. This is the set theoretic part. You assume that there are omega squared wooden cardinals. Then you get determinacy for sigma 1 games of length omega cubed. And then there's the game theoretic or recursion theoretic part, where this gives you a model of cryptoplastic plus ADR.
Why do you think containing R? You said that AD already includes that R.
No, yeah, but what I mean is you're living in a ZFC, and you have the real numbers.
That numbers that come from ZFC.
Right.
The ZFC model should be.
Right.
Them should be there,
Mhm.
not some strange copy.
Right. So they're not. These are the actual real numbers. So in a way, it's a bit stronger, or it feels a bit stronger.
Yeah.
Very strange ordinals, omega square, omega cube.
Yes.
So what if you consider epsilon nulls outright or something?
Well,
Or even maybe something easier like omega square plus omega. Would this give anything interesting? Or?
I think so. It's hard. Sometimes here the theorems, it's obvious what they should generalize to, but then the proofs have to be very different, which is nice, I think. There are some general facts known. There's Theorem of Niemann that says that if there are, let's say, alpha wooden cardinals, then and measurable above, then games that are of length omega times alpha with pi11 payoff are determined. So actually, if you assume a measurable cardinal above these woodens, then this theorem was known before in a stronger form. But you can't get this conclusion only from... Sorry, you can't get the stronger conclusion without the measurable. So this is a theorem that has a weaker hypothesis and gives you a weaker conclusion. So in general, it feels like the picture should generalize everywhere. So I want to talk about this. So we'll see where the omega cubed comes from. And the main tool we will use to prove the theorem or to sketch its proof is the theory of inductive definitions. What time is it? So you can look at sets of natural numbers defined inductively by some operator, but you can also do that with the real numbers. And we will look at sets defined inductively using what is known as an abstract quantifier. So a quantifier is quantifiers on the real numbers. It's a collection of subsets of R, which is, I guess, not empty. And closed under supersets. So an example is the existential quantifier. Is just the collection of all subsets of the real numbers which are non-empty. So you can think of saying A belongs to the existential quantifier if and only if there's an x such that A of x, when you think of A as a predicate. And actually I will use this notation. Another example is the real game quantifier, which is the collection of all sets of reals such that player 1 has a winning strategy for the game on reals with payoff A. So, and also the notation is games reals x, A of x. So this expression means that if you...
Excuse me, payoff set, it has to consist of sequences.
Right, but I'm abusing notation because countable sequences of reals, we can fix some coding that codes omega length sequences of reals by single reals. So sets of omega sequences of reals we can think of as sets of reals. Yeah, I'll incur in these abuses of notations.
But still we play the game on reals.
Right.
The same has also meaning when we play the game on integers. Sequence of integers is real as well.
Right. So that was real. This is also real, yeah. So when we write games reals x, ax, it means that if you look at the game with pay of x, then player 1 has the winning strategy. So another example would be the dual quantifier. Actually, you can do this for every quantifier. You can write dual qx a of x if and only if it is not the case that qx complement so the dual.
And actually write negation there.
Yeah, let's do that. So the dual of the existential quantifier is the universal quantifier. The dual of this quantifier would be, it's not the case that player 1 has a winning strategy for the complement. So you can think of these games as saying player 2 does not have a winning strategy. If the game on A is determined, then you can push negations inside the quantifier and replace it by its dual. So an observation is that because quantifiers are closed under supersets, we have that x belongs to Q if and only if there's a y in Q such that y is a subset of x. So this looks like a silly observation. So this is the same as saying there's a y in Q such that for all x in y we have x of x. So it seems like I'm saying nothing, but the point is that because of this we can define expressions such as this one: q0 x0, q1 x1, q2 x2, and so on. X of a sequence x0, x1, x2, and so on. We can define expressions with an infinite string of quantifiers if player 1 has a winning strategy in the game where, well, we replace the first quantifier in this way. So player 1 starts by playing some element of it, some y0 and q0. And then player 2, the universal player, plays some x0 and y0. And then you go on to the second quantifier, y1 and q1. And then player 2 responds with an element of it. And so on. And then at the end, 1 wins if and only if the sequence produced belongs to X. Again, thinking of this as a single real. Keep this one.
This theory of general quantifiers is 100 years old.
100.
Yes. Its founder was, by the way, Kolmogorov. In the form of operations. So there is a paper of him dated probably to 1920 or something like that. Not recently, but discovered more or less like 20 years ago and published in second or third volume of his.
Mm-hmm. And that was about these operations like Alexander,
That was a particular case.
Mm-hmm.
And he also discovered this dual operation,
Mm-hmm.
which is the same as the double negation. Okay, I'm sorry.
No.
Just historical remark.
That's good, because I thought it was from the 70s. So, but now I know that I'm in the right place to talk about this. By the way, to find the right chart.
Take the chocolates on the table.
Yeah, it won't last longer. Let's see. Games reals x, a of x, is the same as there's an x0 for all x1, there's an x2, so on. And, well, you can prove this using the definition we gave, but this is what you would expect, because this is saying player 1 has a winning strategy in the game on A, and this one is saying player 1 can make some move such that for any move player 2 makes, player 1 can make another move, and so on, and eventually get the sequence to be an A. So the definition makes sense. Let's see what my notes say. So we will look at sets definable inductively using a quantifier. So an operator is a function phi from the power set of the real numbers to the power set of the real numbers. And we can iterate phi. So phi 0 is the empty set. Phi less than alpha is the union of all the previous stages. Phi alpha is phi applied to phi less than alpha. Phi infinity is the union of all stages. And we say that this is the set defined inductively by phi. But now I want to look at operators.
Could be monotone,
It could be monotone, but
but you don't assume.
if it's monotone, then it has a simpler definition. Actually, I will assume that they are, but it has a simpler definition because you just apply it to the previous stage every time. In general, it doesn't have to be. So what kind of definability are we looking for? We will consider the language LQ of second order arithmetic with constants for each real. Quantifiers Q, and we might throw in the dual for free. And a new third order predicate symbol let's say x dot. And we will consider operators of the form x goes to the set of all reals small x such that something holds of them when the constant x dot is interpreted as x. But we want some restrictions on the formula psi. For psi, in which the constant x, thank you, appears only positively. Then it will be monotone. So, how this is readable. So we look at operators that take a set and do something to that set that is definable by a formula in the language. Right. So you can use Q to say things about the set and decide which elements belong to the set you're defining.
What is small x and capital X?
This is small.
X with dot as well. So
This is capital X.
And the last one?
This one is,
capital X.
yeah.
And that one is X with dot.
This one, yes. So that one is capital, but I might switch to different letters in the future. So these sets defined inductively by these operators are called Q-inductive. And the class is called IndQ. So, one definition. We say that A, the subset of the reals, is Q hyperprojective if both A is Q inductive and its complement is Q inductive. So the simplest case of all this is when Q is the trivial, or the existential quantifier. And then these are just sets that you can define inductively by first order things over the natural number. There was another one, but I forgot. I think it was this one. And this has an analog for the natural numbers. So suppose we were working with the natural numbers instead. Then what are the sets you can define inductively? Those are the pi11 sets. And which are the sets that are both pi11 and their complement is pi11? Those are the delta11 sets. So these sets are like analogs of the pi11 sets. In particular, the inductive sets without Q are a very natural analog of the pi11 sets for the real numbers. And well, if you look at the delta11 sets, these are precisely the sets of natural numbers that occur in L omega 1 ck, which is the smallest admissible set. Admissible means it's a model of Kripke-Platte. So the same way, the hyperprojective sets without Q are the sets of reals that appear in the smallest admissible set that contains the reals. And you can generalize this for arbitrary quantifiers. So there's a theorem. Oh, this is such a good chalk. This is the best one so far. It's a theorem of Moskva. It's called the companion theorem. I'll just state it this way. Let Q be a quantifier. Then there is an admissible set M containing R whose subsets of R are precisely the Q hyperprojective sets. So actually there's a big theory of inductive definability. And so what you do is there's a notion of what's called a spector class on the real numbers. And an example of such classes are the Q inductive sets for any Q. That's the theorem of Axel. And then Moskvakis, the real companion theorem is that for every spector class, you can find an admissible set whose subsets of reals are precisely those in the self-dual part of the spector class. And conversely, whenever you have an admissible set containing the reals, you can find a spector class whose self-dual part is that admissible set. But I think this is all we need for now.
But this depends on the choice of Q, right? So if Q is very strong, then we sort of get bigger and bigger admissible.
Right.
Something like that. Mm-hmm.
Mm-hmm. So, let me see. What do my notes say? Okay, so we need two more definitions, but they're short. The first one is really more an issue of notation. So I will write QA, so Q is a quantifier and A is a set of reals, and I will use Q itself as an operator for the set of all reals X such that the set of all y such that the pair xy belongs to A belongs to the quantifier Q. So let me make a drawing, which will be easier to read.
Like sort of projection.
Right. Well, in the case that Q is the existential quantifier, it's really a projection. So you have A here, subset of the plane. You have the x-axis and the y-axis. And you look at all the x such that this section of A belongs to Q.
Sufficiently large.
It's large in the sense of Q, right? If Q imposes the least possible restrictions, just being non-empty, then it's really a projection. So it's a Q projection. And there's a theorem of Axel theorem of Axel, which says let Q be a quantifier and then he defines what's called the next quantifier, which is called Q plus, by setting Q plus x A of x if and only if. And then we will have a familiar picture here. Q x0, Q dual x1, and then you put an existential quantifier and then a universal quantifier to avoid pathologies. And then you just repeat this. Q, Q dual, so on. And that belongs to A. So this generalizes the game quantifier, because if Q was the existential quantifier, then Q plus, this is existential, universal, existential, universal. It generalizes the game quantifier. And that's called the next quantifier. And I haven't stated any theorem. So then the Q inductive sets are precisely the Q plus projections of projective sets, of sets that are first order definable over R with parameters. So now we have a characterization of the inductive sets in terms of the next quantifier. We also had the definition by induction. And well, we also know that, I don't know if the things I stated are enough, but if you take any admissible set closed under Q, then if you present it the right way, then the sigma 1 sets relative to that set will be the Q inductive sets. And so now I think I have everything to prove this theorem. Check my notes, that I don't forget anything. Okay. So, let me check the time. Okay. Are there any questions before?
Which years was it? It was by Excel, 70s, 80s?
It is 75-ish.
Actually, this sequence is more or less or similar to what Kolmogorov defined as art and form.
Uh-huh.
And what is the role of this intermediate first order quantifiers in between?
I didn't actually think about it. So, I don't actually know if you use it in the proof of this theorem or just in other things that use this definition. Or maybe the way I define quantifiers, you don't really need it. In our case, I will look at quantifiers like the ones that I've defined, like the game quantifier and the existential quantifier. And those all absorb the existential quantifier. So you can actually remove
Maybe
this.
if this Q is already stronger than existential quantifier,
Right.
then this can be avoided.
Right. And that will be the case in what we will do.
Okay.
But maybe if you were careful enough to define things the right way, then you can always avoid it. So I'll see how to prove that theorem. Almost. And I'll see. Proof sketch of theorem C. So the key is to consider the quantifier GR, I'm going to call it GR omega squared, which is all the subsets of the real numbers such that player 1 has a winning strategy for the game on R with payoff A. The game on R of length omega squared. So we look at a game where players play real numbers for omega squared many moves. This produces a sequence of omega cubed many digits that we then code as one single real number, and we ask whether that belongs to A. And this quantifier collects all the sets for which player 1 has a winning strategy. And so if this theorem were a homework exercise, the hint would be consider this quantifier. And then everything will flow.
Well, this is just the most natural game quantifier for omega square length.
For games on reals.
Okay.
So if we look at it as an operator, games reals omega squared A is, so what was it, the set of all x such that player 1 has a winning strategy. I'll just write wins. The game on the real numbers of length omega squared in the set all y such that x comma y belongs to A. So it's like A gives you a R parameterized sequence of games, and then you select the ones that player 1 has a winning strategy for, and that's what the operator gives you. So the first lemma is, well, suppose star, that's our determinacy assumption. Oh, by the way, just like we can apply G to a set, I could apply it to a class in the sense of I will write GR omega squared sigma 1 for the set of all GR omega squared A, where A is in sigma 1. So the lemma says, suppose our determinacy assumption, then games of length omega squared with moves in the natural numbers with GR omega squared sigma 1 payoff. Oh no. Are determined. So we take a game of length omega squared in this set. How do you prove it? Well, if A belongs to GR omega squared sigma 1, then it has to be of that form. Then there is a sigma 1 set B such that A is set of all x such that player 1 wins the game of all y such that xy belongs to B. So suppose you had a game of length omega squared on the natural numbers with payoff here. I want to simulate that game by a game of length omega cubed on the natural numbers with open payoff. So the way to do that, the way to do that is we consider a game where the two players begin as though they were playing game A. So they play x0, x1, x2, and so on for omega squared many rounds. And then, well, you would want player 1 to win this game if this move is here. So instead of directly asking a complicated question, namely whether player 1 has a winning strategy in this game, you will ask player 1 to show that she has a winning strategy. How do you show that? Well, you ask them to play the game out.
Where omega cube appears?
It hasn't appeared yet.
Not yet.
Well, not in an obvious way, maybe. It's lurking. So then, afterwards, they will play. So these are natural numbers. They will play real numbers y0, y1, y2, so on. For omega squared rounds. And at the end, this produces a sequence x0, x1, x2, and so on. y0, y1, y2, so on. So this produces this sequence, which I'll just bundle as xy. And then the payoff is player 1 wins the game if and only this bundle xy belongs to B. So this payoff is, we're asking whether something belongs to B. So it's a sigma 1 payoff. And the length of the game is, well, you start out by playing omega squared many natural numbers, and then omega squared many real numbers. So the total length is omega squared plus omega squared times omega. So that's omega squared plus omega cubed, which is omega cubed. So this is a game of length omega cubed with payoff sigma 1 set. So it's determined. And the point is that if you look at any winning strategy for this game for either player, and you just restrict it to the first omega squared many moves, then that's a winning strategy for A. Because you play by that for the first omega squared many rounds, well then you've produced an X such that you still have a winning strategy for the rest of the game. So you have a winning strategy for the game on B. If you're player 1, then this directly shows that that X belongs to this set. If you're player 2, then it shows that you have a winning strategy for the complement of the game, so player 1 can't have a winning strategy for the game. So any strategy for this auxiliary game restricted to the first omega squared many rounds is literally a winning strategy for the game on A of length omega squared on the natural numbers. So I didn't write everything down, but that was the proof.
So the x's are omega
The proof
square
lemma.
many, the x's are omega square many, and then there are these real numbers y's.
Right.
And there are also omega square many
Right.
of those.
So, but instead of asking them to play the real numbers, you ask them to play digit by digit.
So you split each real move into a sequence of integer moves.
Right.
So where will there be omega cube of them? So if you digit by digit decipher this y's, that
Right.
will be omega square. That would be omega cube.
Right.
Because omega square does not.
Because it's
The
added
initial part
from the left.
is smaller anyway.
Mhm.
And omega cube that will be there. Why didn't you then? Why couldn't you, in the same way, get omega cube?
Because then it would be a game of length omega cubed times 2.
Plus omega cube. Okay, it should be less than omega.
Right.
Anything less than omega cube.
Right.
Okay.
And actually you could ask whether this assumption implies determinacy for games of length omega cubed times 2, but it doesn't. So that proves this lemma. The converse of the lemma is also true. That takes a bit more work, but we don't need it. So where is this going? We have almost all the pieces now. We just have to fit them together. It's a lemma 2. The inductive sets relative to the real game quantifier, the usual one for games length omega, these are contained in the games reals omega squared sigma 1 sets. Alright, so these are sets that you look at operators defined by the simple real game quantifier, and then you inductively define sets. Before proving this lemma, I'll tell you how to get the theorem from it. This is also an equality, which we don't need. Suppose that games of length omega squared on the natural numbers with who lived a good life.
Isn't that from the
One of
Yes, but yeah, with games reals hyperprojective payoff. Suppose that all games of length omega squared on the natural numbers with games reals hyperprojective payoff are determined. Then every games reals hyperprojective game on reals, these are also determined because you can simulate them by games of length omega squared on the natural numbers in which you play the digits. But the point is that they have a simple winning strategy. A games reals hyperprojective winning strategy. So this lemma is proved by induction. So the games reals hyperprojective sets are generated inductively using inductive definitions on the real game quantifier, and you prove this by induction. It uses something that's called the third periodicity theorem of Moskowakis, which is it uses the proof of that theorem, which is it gives you results of that form from the natural numbers, but now you do it for the real numbers. So now that we have all the pieces, we can prove the theorem.
Is it similar in some sense to Borel determinacy, how it is put or not?
Well, but this already assumes determinacy, and it gives you that there are simple winning strategies. Mm-hmm. And this is a frequent phenomenon. For example, pi 1 1. Let's say you have predictive determinacy. Then every predictive game has a predictive winning strategy. So
that's more. So the analog of this without game quantifier would be indeed pi 1 1 determinacy or something like that, right? So pi 1 1 determines set. So the simple version of this argument would be what? So if
sigma 1 2 games, if they are determined, then
there is a simple.
Then pi 1 1 games have a sigma 1 2 winning strategy. So, well, what do we need to prove? We need to find a model of Kp plus ADR containing the reals. So we will apply the companion theorem. Apply Moskowakis' companion theorem. To find an admissible M whose subsets of R are the games reals hyperprojective sets. So now we have sigma 1 determinacy for games of length omega cubed on the natural numbers. So by the first lemma, we have determinacy for games reals omega squared sigma 1 games of length omega squared on the natural numbers. By the second lemma that I haven't proved yet, when we have that games reals inductive sets are determined. Actually, games of length omega squared in games reals inductive sets are determined. Well, those sets contain the games reals hyperprojective sets. So the third lemma tells you that games reals hyperprojective games on the real numbers have games reals hyperprojective winning strategies. So this means that every game on reals in M, those are games reals hyperprojective, has a winning strategy in M. So by the lemma, M satisfies ADR. And that proves the theorem modulo the two lemmas. So it's 8:12. I'll just say something about how to prove the second one. And because the intuition is very simple, I mentioned Axel's theorem that characterizes the games reals inductive sets in terms of the predictions of the next quantifier. So by Axel's theorem, every A in games reals inductive is of the form games reals plus applied to B for some B in some pi 1n. Thus, a number x belongs to A if and only if games reals x0, games reals dual x1, games reals x2, so on. And then you ask something pi 1n about that sequence, and x, and maybe some parameter. Well, just to make the parameter. So to check that this set belongs here, we would like to determine membership in A by playing a game on reals of length omega squared with a sigma 0, 1 payoff. And that game would be well, it would be something like you start playing this game where here, instead of to determine whether player 1 has a winning strategy in the remaining of the game, you ask them to actually play out the game. That takes you omega many real numbers. Then you move over to the next one until at some point player 1 decides that she has enough information to witness membership here. Oh. So I defined the next quantifier wrong. It should have been there exists a k such that B of the first k many numbers played. So you start playing out this game quantifier by quantifier until at some point player 1 decides that she has enough information to win, then tells you which k it is, and then you have n many rounds where you witness these quantifiers to show membership in B. And this is a game that if player 1 wins, then it takes fewer than omega squared many rounds, but maybe player 1 never wins and the game goes on forever. So it takes in general, it's a game of length omega squared on real numbers. And the payoff is sigma 1, if you look at it carefully. So this takes some work to get out the details, but that's the intuition. Yeah. So.
Okay.